Chapter 5, question 143. The question for all the parts A through E is asking us to evaluate each of the following limits. For part A, we are going to start by factoring the top of the limit, so make sure you write the limit as x approaches 2 again. Then that is equal to x minus 2 times x squared plus 2x plus 4 all over x minus 2. And excuse me, you do not have to write the equal for the limit in front of it. So then once we do that, you can see that we're able to cross out this x minus 2 and continue with the limit. So now we have the limit of x minus 2 of x squared plus 2x plus 4. Now we can plug in the 2 as x approaches 2. Now we can plug in the 2 and go 2 squared plus 2 times 2 plus 4. And now we don't need the limit because we plugged it back in and we get 12. Part 3 says the limit of x as h approaches 0 is secant of 3 times x plus h minus secant of 3 times x plus h all over 2h. We know that this is the definition of the derivative, so we know that this is all equal to f prime of x. Because we know that this is the definition of the derivative, we can take this part here, because we know that is the definition of the derivative, and we then can use that to say that f of x is equal to secant of 3x. Then using the derivatives of trig functions, we know that f prime of x is equal to secant 3x times tangent 3x times 3, because we have to use the chain rule in this part. So then we can continue on and break this down even more and say that it is equal to 3 secant 3x times tangent 3x. This is your final answer to the part B. For part C, we're evaluating the limit as h approaches 0 of cotangent of pi over 4 plus h minus 1 all over h. We can break this or expand this a little more and say that it is now the limit as h approaches 0 cotangent of pi over 4 plus h minus cotangent pi over 4 and all over h, in order to make it look like the definition of the derivative. We can then go further and say that this whole equation is equal to f prime of pi over 4. From this we know, because it's the definition of the derivative, that f of x is equal to cotangent of x. So f prime of x is equal to negative cosecant squared of x. This is again using our trig identities. Then we can plug in f prime of pi over 4, which we got from the definition of the derivative when we plugged in 0. And we can plug this f prime of pi over 4 equals negative cosecant squared of pi over 4, which is equal to negative 1 over sine squared pi over 4, which is equal to negative 1 over square root of 2 over 2 squared equals negative 1 over 2 over 4 equals negative 1 over 1/2 equals negative 2. Part D is asking the limit as x approaches pi of tan of 5x over x minus pi. Again, if we plug in pi, we get tan of 5x over 0, which doesn't work. So what we're going to do is evaluate further by making this equal to the limit of, as x approaches pi, of tan 5x over tan of 5x minus tan of 5 pi all over x minus pi. When you plug in tan of 5x, or tan of 5 pi, it's equivalent of minusing 0. This is equal to f prime of x. Using the definition of the derivative, we again know that f of x is equal to tan 5x. And I wrote f prime of x, but we're actually only looking at f of x. I said that f of x is equal to tan 5x. So then we know that f prime of x is equal to secant squared 5x times 5, based off of using the trigonomic functions and the chain rule, because this is a tan of 5x is a chain, so you have to identify 5x as its own blob. Then we can plug in f prime of pi, which is what we're getting from our original equation, and we can see that it's secant squared of 5 pi times 5 equals 5 over cosine squared 5 pi which is equal to 5 times over negative 1 squared, which is equal to 5. That is our final answer. Then to answer the question from part E, which says, what do all these limits have in common? We know that all these limits were limits that looked at the derivative of some type, because we use the definition of the derivative for x at a certain point.